Here's another application of refraction. I'll go around the room right now and I see two of you with glasses on. Anybody have contacts in right now? So right now there's only 9 of you here today. 4 of you have either contacts or glasses. So basically half of you. Count me, that's 10 people. I have glasses. That's half of us need corrective lenses, right? Why do we need corrective lenses? Well, because the lens in our eye, generally it's because the lens in our eye doesn't work quite properly. The lens in our eye is a material other than air. When light goes through that lens, that convex shaped lens, it bends. It bends so that it focuses on the retina at the back of our eye. If it's not bending properly, it's not the right shape, the light isn't going to bend properly. It's not going to refract properly and focus in the right place. We need corrective lenses to bend the light more, to bend the light differently, to fix the problem with the bending of light that the lens of our eye has. Lenses bend light. Refraction is the reason why lenses bend light. There are 2 kinds of lenses, 2 general kinds of lenses. There's other specific subcategories, but 2 general kinds of lenses. One's called a convex lens. Okay, you can see an example of a convex lens right here. It's a magnifying glass. Okay, you want to magnify text, use a magnifying glass. Basically, if you need reading glasses, you need magnifying glasses. You need to magnify text. When you hold a newspaper up in front of your face and you can't read it, you need magnifying glasses in front of your eyes in order to read it. So those are reading glasses. The other kind of lens is what we call a concave lens. If a convex lens is thicker in the middle, like this, okay, looking at it from the front, it's a magnifying glass, then a concave lens is thinner in the middle, looks like this. This is what I'd be willing to bet all of you that have corrective lenses or contact lenses have, is concave. The reason why you're likely to have concave lenses to fix your eyesight is because you can likely see nearby. At your age, even at my age, I can read a newspaper if I hold it up in front of my face. I can't see far away. I can't see what it says on the board if I stand at the back of the room. Okay, I'm nearsighted because I can see near. I can't see far. The rays of light normally, for me, focus in front of my retina. They come together right there. I don't want them to focus in front of the retina because by the time it gets back to my retina, which actually detects the light, the rays are kind of spread apart again. That means that I see a blurry patch. Right? That's what I see is blurriness because the rays of light aren't focusing at the right spot. So what do? I get a concave lens in order to spread the light out a little bit. This diagram isn't very good, actually, just looking at this again. What it does is spreads the light out again. It bends the light, spreads it out, so that by the time it goes through the lens of my eye, it converges a little bit further back on the retina of my eye. 2 kinds of lenses. Convex, which we also call converging, by the way, because it causes light rays to come together. Or concave, which we also call diverging because they cause light rays to spread apart, to diverge or to spread apart. Now, we talk about lenses as being an application for refraction, and they are. But there's lots of applications even within lenses. We talk about the magnifying glass. Saw this picture a couple of years ago. Remember when Chris Hadfield was the commander of the International Space Station? You guys remember this, right? He was tweeting photos every day and putting photos on Facebook every day that he took from space. Okay, I got this one day and I thought, this is perfect. He took a picture of this droplet of water, or somebody took a picture of this droplet of water in front of Chris Hadfield's face. What do you see in that droplet of water? First of all, the shape of it. It's perfectly spherical. Why? Unless it's moving around, if it's just sitting there, it's perfectly spherical. Why is it perfectly spherical? Usually water droplets are more teardrop shape, right? Why is this not teardrop shape? Because there's no gravity. You can't have a teardrop shape when there's no gravity, right? That's what causes that teardrop shape. So you get this perfect sphere in front of his face. What do you see inside that perfect sphere? That droplet of water in front of his face. You see his face. You look through it, you see his face. But look at the characteristics of his face. What do you notice? I can see both eyes and his nose in there. But his eyes are smaller, his nose is smaller, and everything is upside down. So lenses can cause things to be magnified. In the case of a magnifying glass, lenses can cause things to become smaller, to shrink in size. Lenses can cause things to be flipped upside down. Why would we ever want to flip something upside down? Well, there's lots of reasons why we might want to flip something upside down. When you go to a movie and watch a movie, anybody go to a movie on the weekend? Go to a movie and watch a movie. The image is flipped upside down. Wait a second. You're saying, no, it's not. I watched the movie. I don't have to turn my head upside down to see the movie. The object, the film that goes through the projector, goes through upside down. So in other words, it gets flipped over to be right side up. The lens that's in the projector flips over the object that you see, which is the film that goes through the projector, and produces an upside down image on the screen. But because the object was upside down, the film was upside down, then the image actually becomes right side up. We're going to learn today, over the next 15 minutes or so, to draw what we call ray diagrams that go along with these different kinds of lenses. A ray diagram shows it can show 3 different rays, or potentially just 2 different rays, which will indicate for us what an image will look like. Okay, what are we going to see as a result of light going through that lens? There are 3 rays that we can draw, 3 rays that are very predictable, but we only ever need to draw 2 of them. We know when we look at a lens, you're not drawing ray diagrams here yet, guys. I just want to show you something on this, okay? You can copy this down in your notes, but don't put it on the template that I gave you, okay? I want you to save all those lenses on the template for something I'm going to show you in just a couple minutes, okay? We know that there are rays of light coming from every which direction that will go through this lens. We want to focus right now on rays that are parallel to this line that goes through the geometric center of the lens, this line that we're going to call the principal axis. Those rays that are parallel to the principal axis will refract through the lens and converge all at one spot. They're going to converge where that dot is. That dot is what we call the focal point. For a convex or converging lens, rays that are parallel to the principal axis will converge at the focal point. Now, there are rays that are going through this lens that aren't parallel to the principal axis, that are coming from every which direction. They converge somewhere else. But we're focusing right now only on the ones that go through that are parallel to the principal axis. They converge at the focal point. Now, the second dot that you see right here, it doesn't really have any huge significance. We're going to call it 2F because it's simply twice the distance from the lens that the focal point is. The rays don't go through there. The rays just go through the focal point. I'm using that as a spacer for the ray diagrams that you're going to draw in a few minutes. Rays that are parallel to the principal axis converge at the focal point. You're going to do an activity in a couple days, another activity in a couple days, where you're going to need to find the focal point of a lens as part of your activity. What you're going to do is take a lens, aim it at some condos across the street, a far-off object, because the rays that are reflecting off of that far-off object, the condos across the street, when they go through the lens, are effectively parallel to each other and parallel to the principal axis. They'll converge at the focal point. You'll see on a little piece of paper on the other side of that lens the image of those condos projected onto that piece of paper. Right, Caitlin? You're going to see the condos on that piece of paper just by shining a light or just by aiming a lens at the condos across the street. Okay, so all rays parallel to the principal axis converge at the focal point. We got a principal axis that goes through the geometric center of the lens. We got another point that we call 2f, which is simply twice the focal length. Okay, twice the distance from the lens to the focal point. One more point that we're going to identify here, we're going to call the optical center. That's the point that the principal axis goes through, the geometric center of this lens. Now, there's a million rays of light that go through this lens. When we want to see what the image formed as a result of a certain object is going to look like, we're going to draw two of them. The reason we draw only two is because we can get away with drawing only two and still get the image characteristics that we expect to get. Why draw 50 if we'd only have to draw two? The first situation that I'm going to try is when we have an object that's way out here. An object. It could be a car. It could be the condos across the street. It could be a picture of you. We have an object that's represented by this arrow, just showing we have a top of the object and a bottom of the object. Right, Devin? That's well beyond the focal point. That's well beyond twice the focal point. It's way out there. What is that image formed as a result of the rays of light going off of that object through the lens? What is that image formed going to look like? The first ray that we're going to draw is a ray of light that reflects off of the top of the object, parallel to the principal axis. Again, there's a million rays of light that are reflecting off of the top of the object. We want to pick the one that goes parallel to the principal axis. Where does it go? This is why we want to draw this one, because we know which way it goes. Every ray of light parallel to the principal axis goes where? Down through the focal point. The second ray of light that we want to look at is a ray of light that also reflects off of the top of the object, but this time goes down through the optical center. That one doesn't go through the focal point. In fact, that one just keeps going straight. It doesn't actually refract. It's not true, actually. It refracts once when it hits the boundary right here, and it refracts again when it hits the boundary right here. But the net effect is that it goes straight through. What's happening inside the lens isn't quite correct. But again, the net effect is on the other side of it. It ends up doing what we have drawn there. So we don't worry so much about what happens inside the lens. We just worry about the net effect. So what does that tell us? Well, if the top of the object, the car, the little kid, whatever it is, if the top of the object is right there where these rays start, then the top of the image is right here where these two rays come together. If the bottom of the object is right here at the principal axis, then the bottom of the image will be right here at the principal axis. If the object is drawn from bottom to top, then the image is drawn from bottom to top. What do you see when you have an object that's, well, as tall as the object we have there, and that object is quite a ways away from the lens? You see an image that's formed on the other side that has three characteristics. The first characteristic is that it's smaller. It's smaller than what we started with, right? You haven't magnified this. You haven't made it bigger. You've made it smaller. You hold up a magnifying glass to something a big distance away from that something. You look through that magnifying glass, you're not going to see anything magnified, anything bigger. You're going to see a smaller image. It's not working as a magnifying glass very well, is it? That's why you have to hold a magnifying glass right in front of the thing that you're trying to look at, not way back from it. Because if you hold it way back from it, it's going to produce a smaller image. The second characteristic is that it is smaller. Sorry, not smaller, but inverted. It could be upside down, inverted, or it could be right side up. Upright, sometimes we call it. This one's inverted. It's upside down. You hold that magnifying glass up to that map on the back wall, but you hold it right here in front of my face. The image of that map on the back wall that I'm going to see after the light is projected through the lens is going to be smaller, and it's going to be upside down. Now, here's the tricky one. The third characteristic relates to whether we call it a real image or a virtual image. This is what we call a real image. A real image is an image that can be projected onto a screen. When you go to a movie, you're seeing the image projected onto a screen. That's a real image. A virtual image can't be projected onto a screen. Well, then how could you see a virtual image? If you can't project it onto a screen like at a movie theater, how do you see a virtual image? You ever use a magnifying glass? Everybody has, right? You read the newspaper, look at some fine print with a magnifying glass, okay, it becomes bigger, right? Are you projecting that image onto a screen like at a movie theater? No. You're looking through the lens to see that image. If it's a real image, you can project it onto a screen. If it's a virtual image, you got to look through the lens to see it. You can't project it onto a screen. Okay, when I go into the bathroom in the morning to shave and to comb my hair and to brush my teeth, I look in the mirror. And that's not a lens, right? That's a mirror. But same kind of analysis applies here. Am I projecting an image of myself onto the wall? Am I projecting an image of myself onto a piece of paper or onto some kind of screen? No. How do I see that image? I've got to look at the mirror to see it. That's a virtual image. If I could project an image of myself onto the wall behind me, then that would be a real image. If I can project it onto a screen, it's real. If I can't, it's virtual. Now, how do we know if we can project it onto a screen or not? Well, here's the rule of thumb. It's not going to make a whole lot of sense to you yet, but it will in a few minutes. If it's solid lines that intersect here, and these are solid lines, not dotted lines, solid lines. If solid lines intersect, it's a real image. If dotted lines intersect, then it could not be projected onto a screen, and it's a virtual image. So how do we see this? Well, we could put a piece of paper or something right here, and we would see an image of whatever that object is projected onto that piece of paper. How else could we see it? Well, we could look through the lens just like this in order to see it. We just don't have to do that. We don't have to look through the lens to see it because we can project it onto a screen because it is a real image. Let's take a look at the second diagram here. In the second diagram, we have our object at twice the focal length, 2f. The first ray that we're going to draw is from the top of the object, and then it's going to refract down through the focal point. The second ray, just like the last time, is going to go from the top of the object down through the optical center. This is my object. This is my image. My object is drawn from the principal axis to where the lines start. My image is drawn from the principal axis to where the lines intersect or finish. Let's look at the three characteristics of this one. Is that image larger or smaller or the same size as the object? Looks to be the same size, doesn't it? It's not bigger or smaller. What's the point of this one? You got an object that's sitting right here. You got to put a lens in front of it, and what do you see? You see an image that's the same size. That's what it is. The image is the same size as the object is. Is it right side up or upside down? It's flipped over. It's upside down, right? It's inverted. In real or virtual, well, it can be projected onto a screen, so it's real. How do we know that it's real? How do we know that it can be projected onto a screen? Because solid lines are intersecting. That's how we know it can be projected onto a screen. Solid lines are intersecting. Next one. This time we're placing our object in a different place again. This time it's in between the focal point and twice the focal point. So we're moving it closer to the lens every time. First ray that we're going to draw is from the top of the object to the mirror, to the lens I should say. Then it's going to go down through the focal point. The second ray that we're going to draw is from the top of the object, down through the optical center, keeps going straight through. If my object goes from the principal axis to where the lines start, then my image goes from the principal axis to where the lines finish, where the lines converge. What's this? Well, we have three characteristics again. Daniel, is it larger, or is it smaller, or the same size as the object was? Take a look at the image here. That line is bigger than what we started with, right? So we're going to say it's larger. Or we can say it's bigger or magnified or something like that. Caitlin, is the image right side up or upside down? Upside down. We can say that's inverted. If you use the term upside down, that's fine. As long as you recognize what it is, I don't care exactly the term that you use. We're going to say it's inverted. Upside down, it's inverted, whatever you want to call it. The tough one, here's the tough one. Is it real or virtual? Tom, do you know whether it's real or virtual? Do you know whether this is real or virtual? Why do you say virtual? Okay, just a guess. Yeah? Why do you say it's real? Good. It's real. And it's real, we know that because solid lines intersect. Now, what makes it real? It's real because it can be projected onto a screen. But how do we know that it can be projected onto a screen? Because solid lines intersect. You haven't even seen a diagram with dotted lines or even on the diagram, right? They're all real so far. You're going to see one pretty soon, though. Next one. This time the object is at the focal point. Not really the focal point, because the focal point's on the other side, but the same distance from the focal point, just on the first side. First ray of light reflects off the top of the object down through the focal point. Second ray of light from the top of the object down through the optical center. Oh, wait. They don't intersect. They're parallel, aren't they? If these lines don't intersect, what do we know about the image that's formed? Or not formed? There is no image. It seems strange, but if you take a magnifying glass and hold it a really, really big distance away from an object, you're going to see what we saw in our first diagram. Right? Where is it? Right there. You're going to see an image formed that's upside down and smaller. As you bring it closer and closer and closer to the object, that image is going to get bigger. It's going to first become the same size as the object, then it's going to become bigger than the object. In all three cases, upside down. But if you keep moving the magnifying glass closer to the object, so that at some point the object is the focal length away from the lens, then what you end up seeing is nothing. You look through the lens, you don't see anything. You can't see an image of the map at the back of the wall if the map is a certain distance away from the lens that corresponds to the focal length of the lens. We still haven't seen a magnifying glass yet, right? This is a magnifying glass, but we haven't seen the characteristics of a magnifying glass. Magnifying glass makes things that are bigger and right side up, not smaller or same size or upside down or no image at all. Take a look at this one. This time our object is really, really close to the lens. It's less than the focal length away from the lens. First ray, parallel to the principal axis, down through the focal point. Second ray, down through the optical center. Hey, wait, these don't converge either. But they're not parallel. If they're not parallel, pay really close attention to what I'm about to say. If they're not parallel, then let's extend them back as dotted lines. Now we have lines converging, but they're not solid lines, they're dotted lines converging. If the object is from the principal axis to where the lines start, then the image is from the principal axis to where the lines converge. Except this time it's dotted lines converging.
Teresa Schreiber, can you come in Mrs. O's office, please? Teresa Schreiber.
What are the characteristics of this image? Maddie, is it larger, smaller, or same size? Is that image that's formed right there bigger or smaller or the same size as the object right there? It's bigger. Is it right side up or upside down? Right side up or upside down? This is an easy question. Devin, right side up or upside down? Right side up. Okay, we're going to say upright. Simon, you know the answer to this one. Is it real or virtual? How do you know it's virtual? Good. It's virtual. We know that because it's dotted lines that intersect. That means you can't project this one onto a screen. So how do you see it if you can't project it onto a screen? How do you see the image through a magnifying glass? You look at the lens, right? You look at the magnifying glass. That's how you see that image. Does that make sense? Okay, we'll wrap it up there for today, and we'll pick up on the back side of that page tomorrow.